Okay, so I think they can rejoin later. So let's see, where did we stop last time? I think we did all this. We did all these examples. This is where we stopped, right? I think there's people still trying to join. Yes. Allow them back. Okay, so we'll start now. I hope you have had a chance to look at the previous work from yesterday. The video was shared as well. If you wanted to watch it again, it's available. So I will just move on to the next theorem. So so this one says the following: if I have two maps which are group homomorphisms, the first one is phi from G to H, and then this is also phi from, it's just a different font for phi from H to K. Then they are group homomorphisms. Then this composition of the two will also be a homomorphism. Remember, the composition will move from G all the way to K, right? So that composition turns out to be a homomorphism as well. The next bit says that if you have two homomorphisms which are actually isomorphism, so that's homomorphisms that are one-to-one and onto, then the composition of the two will also be an isomorphism. You can hear me?
Yes.
Good, good. So then the third one says if a homomorphism, if you have an isomorphism phi, then its inverse must also be an isomorphism. So we will prove them one by one. So let's look at the first one. The first one says the composition of two homomorphisms is also a homomorphism. So we'll go ahead and look at the proof. So suppose we have two elements in G, then this composition, since it takes elements from G to K, it will act first on the elements from G. So if we try to get the image under the composition of this product, XY, just apply the rules of composition of functions. Now, I think I'm using a different symbol again. This symbol here, I have replaced it with a different one, this one. So just think of this as the one you see here. This symbol is precisely this function, this one. Are we together? I will change it again. I didn't notice this. So this composition, if you just use the rules for composition of a function, it means this the image of xy under phi becomes the argument for this function. And since this phi is a homomorphism already, you can split this into two as the image of x multiplied by the image of y. That's true because phi is a homomorphism. And then you can change this again, phi. Since this psi is also a homomorphism, in our theorem it's phi, so I'll just call it phi. So since phi is a homomorphism, you can split it into two also. You can have phi acting on this and phi acting on this again. So this proves that the composition is also a homomorphism, because you have the composition acting on X multiplied by the same composition acting on Y. So that is all you need to check to prove that the composition of two homomorphisms is also a homomorphism. So the next one says what we are doing is checking if a homomorphism is an isomorph. The composition of two isomorphisms is an isomorphism. So we have assumed that both both of them are isomorphisms, so both of them must be one-to-one and onto. That is, they must be bijective. So we shall use that property. Bijective means both injective and surjective. So if the composition, the image of the X under this composition is equal to the image of Y under this composition, this means we can apply these rules for composition of functions, and this phi of X becomes the argument here, and phi of Y becomes the argument here. But since this map is already an isomorphism, it means the map is injective. So it means the argument must be equal. So that means the image of X under phi must be equal to the image of Y under phi. But also we know that this phi itself is an isomorphism and therefore must be injective. And this implies that it means that X must be equal to Y. So for that reason, we can conclude that the composition is injective. So also we need to check that the composition is surjective. So since both maps are isomorphisms, they must both be surjective individually. So we just need to check that the composition is also surjective. So because the phi is surjective, for any element you pick from K, remember phi, this map was from what? It's from H to K. This one was from G to H. So we consider this first. If you pick any K in the image of this map, this first map, because it is surjective, there must be an element in H which is mapped onto it. And also because phi is surjective, there must be an element X that is mapped onto this A. So there should be an equal sign here. So both are a result of these two maps being surjective. So we can check if the composition is surjective. It means if you pick any K from the image of the composition, where we can show that X is the pre-image. And that is shown through this computation and using the ideas we have from the previous statement. So we have shown that any K you pick from the domain, the codomain rather, you can always find a pre-image in the domain. The pre-image is X. And for that reason, we can conclude that this composition must be surjective. So we have shown that the composition is both injective and surjective. And therefore, we must conclude that it is an isomorphism. Okay, let's admit some people. Okay. So are we together so far? So now we must conclude that the composition will also be an isomorphism because it's both surjective and injective. So the third one says that if the map is an isomorphism, then its inverse must also be an isomorphism. So if we suppose we have some two elements, A and B, in the image of this map phi, which we claim to be an isomorphism, then of course, since it's one-to-one and onto, the map is invertible. What we need to show is that now that inverse is also an isomorphism as well. First of all, for it to be an isomorphism, it must be an homomorphism. So let's check if the inverse behaves like a homomorphism. So if you want to get the pre-image of this product of A and B, it will be A and B. A is already the image of X and B is the image of Y. So you can simply make those substitutions here. Replace A with the image of X and B with the image of Y. Now this map is a homomorphism. So it means you can bring X and Y back into the brackets here. That is because the map is a homomorphism. Being an isomorphism, it is automatically a homomorphism to begin with. Now, the composition of any map and its inverse will give you the identity, right? So the image, this composition now will give you XY. It will map anything to itself. So XY will simply be sent to XY. But X is precisely the pre-image of A, right? Because A is mapped onto X. And Y is the pre-image of B under this map. So we have shown that this pre-image of the product of A and B is equal to the product of the pre-image of A and the pre-image of B. So it means this map, the invertible map, is a homomorphism. And the inverse is also usually bijective, right? So it's a homomorphism that is one-to-one and onto, and therefore it must be an isomorphism. Are we together up to that point?
Yes.
Good. So make sure you read this very carefully because we will be asking questions that require you to use this information. So this one tries to illustrate what we were doing. If you have two maps, there's this map and there is this one. This one is from G to H, and this map is from H to K. So the composition would send everything from G all the way to K. So that illustrates what the composition looks like. So this is just illustrating the second part, which says the composition of two isomorphisms is an isomorphism, but it can also help understand the general case of a composition of two homomorphisms. So this one shows you the longer step. This one is compressed. The composition simply moves from G to K. This one shows you the steps. So I will have to change I think I'll change the map because this handwritten one I cannot change easily, or unless I scan it again. So I'll change the map in the theorem to use this symbol. It's called psi. So are there any questions on this? Are there any questions on this?
Yes, can you please explain on that map?
This map is simply repeating what we have done on this end. You see let's go back to the so we have these two maps. This one map sends you from G to K. The second map is from H to K. So the composition now will be a map that sends you from G all the way to K, right? And so on. So in the diagram there, we have the map. There's one map which takes you from G to H, that is this phi, and this psi takes you from H to K. So if you get the composition of, since now this means this psi will act first, followed by phi. So in the composition, this psi is what appears first, followed by phi. It will pick this X and send it all the way to K. But since the second theorem, the second part of the theorem rather, is talking about isomorphisms. So it means any element A here you pick will have a preimage X under this map, phi. And any element K you pick from this group K will have a preimage A. So eventually any K that you pick from here, from K, will also have a preimage X under the composition. So if you start from K, you can always find an X in G, which is mapped onto K by the composition of the two functions. So that guarantees that if the two are isomorphisms, then the composition will also be an isomorphism. Does that answer your question?
Yes.
Good. So now we talk about automorphisms. So automorphisms, remember we defined this. Automorphisms are the homomorphisms from G to itself. Now it's possible to define several automorphisms on the same group, and when we collect all those different automorphisms, we represent them using this shorthand. So this means the set of all automorphisms of G. So that's homomorphisms which have isomorphisms rather from G to itself. Any isomorphism from G to itself is called an automorphism. So here what we have is a set of all automorphisms from the group to itself, because it's possible to define more than one automorphism on a group. So suppose we pick any three automorphisms, then the following happens. The composition of the two automorphisms will also be an automorphism. This follows directly from the theorem we proved before, because an automorphism is just an isomorphism, right? But so we showed earlier that the composition of two isomorphisms is also an isomorphism, and therefore this will hold. And from your basic mathematics, you know that the composition of functions is usually associative, so we can take the second property to be true from your knowledge of composition of functions. Now there's a special map called the identity map from G to itself, which is also an automorphism. So it picks any element and sends it to itself. So X is sent to X for any X that is from G. Now this it happens to be an automorphism, and if the composition of this identity map and any other automorphism leaves the map intact. So if you compose phi with the identity map I, you will get phi. So it behaves like the identity element in a group. And we also saw earlier that if phi is an automorphism, in our case we check that if a map is an isomorphism, then the inverse will also be an isomorphism. So, but in this case, an automorphism is definitely an isomorphism and will automatically work also under those conditions. So and also if you compose the map and its inverse, you will always get the identity map, right? So just the inverse function or the inverse map of phi is its inverse under this composition of functions. So under this operation of composition of functions, we can conclude that the set of all automorphisms of G is a group under the composition of functions. So the elements here are functions. Just the same way we were doing this, we learned how to do composition of functions when we were working with the dihedral groups of degree 3 and 4. The symmetries of a square and the symmetries of an equilateral triangle. So this is not entirely new, using functions as elements of a group. So this is called it's a group, the group of automorphisms of G. So we can study some ideas that will help us understand automorphisms. So there's a special homomorphism here, which we should talk about in a minute. Let me just admit. So there's a special automorphism here, which we want to study. Let's define it faster. So G, we have G is a group, and we get some element from G. So we define this map. G is a fixed element, so G doesn't change. This small g is a fixed element. So we define the map with subscript G. This phi subscript G is a map. We define the map as if it acts on X, the image will be G, X, G inverse. So G is fixed, but what is changing is X. X will run through all the elements in G. So this will be a map from G to itself, because these are all elements of G. So when you get a product, you still get an element in G. So the claim here is that this map is an automorphism of G, and it has a special name. It's called the inner automorphism of G, capital G. Usually one more statement is added. The inner automorphism of G determined by this small g. Please put off your microphone. Okay, so we continue. We want to prove that it's a homomorphism. So if we pick any two elements in G, then YG, this image of XY under this automorphism, or rather this map, will be given by this. That's how we define the map. Any element you give it, it will do this exactly. Multiply by G on the left and G inverse on the right. So that's exactly what we have done. Multiply by G on the left and G inverse on the right. But we can insert the identity element in between X and Y in this form, G inverse G. G inverse G is just the identity element, so it doesn't change anything. And using the associativity of the binary operation in the group, in the group, because this is the product of the elements in the groups. You can just the elements in the group, you can just put your brackets anywhere. So when you split it like this, you can clearly see that this is the image of X under this map, and this is the image of Y under this map. And you can write this as a product of the image of X and the image of Y. So this map is a homomorphism. You see, initially we want to show that it's an automorphism, but first it must be a homomorphism. Then we must show that it is one-to-one and one-to. So far we have shown that the map is a homomorphism. It satisfies the required property to be a homomorphism. So that's a conclusion we have made. So we now need to check that it's injective. I think I forgot to split this slide into two. there's a section here which shows you that this map is injective. So for now, we shall just assume it is injective. I will fix that section when I share the slides. There's more after this statement that I didn't split this slide into two, so the information cannot fit on that slide. It is cut out. But now the next statement shows that the map is surjective. So surjective simply means if you pick any element in G, so this X element from G, you can find a preimage under this map. So G inverse XG will always be mapped onto X. So any element I pick from the group will always have a preimage. We have shown that by applying the map to this preimage, and it gives us X. So this will always be possible for any element you pick from the group. So this guarantees that the map is surjective. And we also assumed earlier that it is injective. It is true, but the proof was missing. It is cut out. Now here we conclude that the map must be an automorphism because it's a bijective map. It's a homomorphism from one group to another, and must therefore be an automorphism. It's called the inner automorphism of G determined by the small g. So let's look at some. Suppose we have two different inner automorphisms. Anytime you switch the element in the group, you get a new homomorphism because you change this subscript, and that's what you use to define the homomorphism. So any time you change this value, you get a new automorphism. So here we have two automorphisms. This should not be G. This should be automorphisms of G, because these are the automorphism of G. They can't be in G. They belong to this set, the set of automorphisms of G. So the correction here is that these two maps belong to this set, the automorphisms of G. So if you get a composition of the two maps, this is what you have. The composition of this inner automorphism determined by G and the inner automorphism determined by H will give us this. The inner automorphism determined by G, and we take the image of X under this inner automorphism determined by H as our argument for this inner automorphism. But this is already known what it should be because the inner automorphism is defined as this. You multiply by H on the right and H inverse on the left. We also know what, now this becomes your argument for this inner automorphism. So this inner automorphism acting on this will multiply it by G on the left and G inverse on the right. And using the associative property for the binary operation in groups, you can put our brackets anywhere. And this GH just remains intact, but H inverse G inverse is the inverse of GH. We saw this in an earlier theorem. Hopefully you are reading, so by now this should not surprise you, that the inverse of the product of G and H is equal to the inverse of H multiplied by the inverse of G, in that order. There's a theorem we did earlier which tells us. But now this is precisely the automorphism of G determined by this product, GH, because the composition of this inner automorphism of G and H, of G, and the inner automorphism of determined by H is equal to the inner automorphism of G determined by the product of G and H. So basically, if you get what this says is that so now we are just considering inner automorphisms, and anytime the product, the composition of two inner automorphisms turns out to be an automorphism as well, because this will just be another automorphism, but now an inner automorphism determined by the product of G and H. So we have established that the composition of two inner automorphisms is definitely an automorphism as well. the other thing we can check is this now is inherited. Naturally, the composition of three automorphisms is associative. Any set of three automorphisms, you can put your brackets anywhere. This again is just inherited from the property of functions that compositions are associative. The identity function also I is an inner automorphism, and it's the inner automorphism of G determined by the identity element. You can think of it as that. And last but not least, if you have any element Y in the image, Y is the image of this inner automorphism of G determined by the small g, then if it's in the image, it means Y must be of this form, because how this map simply does this. So anything that is in the image must be of this form, where X is in G, the group G. This small g is a fixed element, the same fixed element we have as a subscript here. So this must be true if anything is in the image. So let's see what happens if you get the inner automorphism determined by G inverse acting on Y. This S should not be there, will be equal to, we already know what Y is, right? So we can replace Y with GX G inverse. Now this is the inner automorphism determined by G inverse. So it should multiply by G inverse on the left and the inverse of the inverse on the right. We saw earlier that the inverse of G is just G. So remember the inner automorphism does this. It simply multiplies by the element on the left and its inverse on the right. So using the associative property, you can always put brackets anywhere you want. So you can group G inverse and G together to get the identity element. You can group G inverse and G to get the identity, which is equal to X, right? So this confirms to you that every inner automorphism is invertible, and the inverse is given. It will also be another inner automorphism determined by G inverse. So every inner automorphism, so the inverse of this map, automorphism determined by G, will just be the automorphism of G determined by G inverse. Now we have checked all the four properties of a group. We have checked closure. We saw that the composition of two inner automorphisms will give you another inner automorphisms at that automorphism in the previous slide. Maybe we can go back. So here we check the first property of closure for a group. If you compose any two inner automorphisms, we get another inner automorphism. We check that it is associative. We found that there's an identity element, which is just the identity map. And every map has an inverse. It must have an inverse in the first place because it's an isomorphism. The only thing we need to confirm is that the inverse must also be an inner automorphism, which is what we have done. And therefore, we can conclude that the set of all inner automorphisms of a group G is also a group under the composition of functions. Okay, are we together?
Yes.
Yes.
Good. So this, again, please try to go over this several times so that it can stick. So here we define another map from the set G to the group, the group G. G is a group, and then we define a map that picks elements in G and sends them to a map, one of the automorphisms of G. So basically the map is defined as the image of G is simply equal to the inner automorphism of G determined by the small g. We claim that this map is a homomorphism under this theorem. and we proceed to prove that. So we simply pick two elements from G and try to get the image under this map, and we see that yes, the image is the inner automorphism determined by AB, because what the map does, picks an element, sends it to the inner automorphism determined by that element. So here it will pick AB and send it to the inner automorphism determined by AB. This AB is a subscript, which is equal to, and we saw earlier that this should be equal to the composition of the inner automorphism determined by A and the inner automorphism determined by B. This one we have already seen how this works. But again, this inner automorphism determined by A is the image of A under this map, and this is the image of B under the same map. So we can conclude that the map is indeed a homomorphism. So we need to find the kernel. Again, this was too. Yeah, we'll just finish with this part. So the kernel of this map is since it's a homomorphism, we usually define, we remember defining the kernel earlier. The kernel is simply the set of all elements in G that will be sent to the identity map. The identity map is the identity element in this group of automorphisms. So that's the description of the center. So it means it will be all those elements in G which are mapped onto the, which behave like the identity map. And if you go further, you will see that that set is precisely this one. To be the set of all X in G such that XG is equal to GX. And this is the center of the group. So this one needs some formatting. So the center here is defined as this. It's a set of all elements in G that commute with all other elements in G. So I'll need to do some formatting here so that the slide looks better, but you get the point. So a center of a group may contain only the identity element, or it may have other elements including the identity element. So remember also we saw earlier, since it's just the kernel of a map, then it may either contain just the identity element, or it can contain other elements as well. And if the center contains only the identity element, then the map usually is supposed to be injective. So if you check, you can go back to your multiplication tables for the dihedral group of degree 3 and degree 4. So you will see that the only element that commutes with all other elements in D3 is the identity element only. So the center of D3 contains just the identity element E. The center of D4 will contain two elements, the identity element and the 180 degrees rotation about the center, positive rotation of the square. So these two are the ones that will, the identity element E will always commute with all other elements, but in D4, you have one more element which also will commute with all other elements. So for any element you pick in D4, this A squared, this element A squared will commute with the element. Now, this one is wrongly written. We should have Z, the Z out here. This Z that is not fancy, not the mathematical Z. The center of the group Z, now the one in here is a group of integers, is just the whole of Z. So I think we will start from here tomorrow. We'll review this, not tomorrow, next week. I will review this section next week. with the slide corrected, and then we proceed from there. So, are there any questions? Hello?
I wish I had the
Enjoy
notes.
your weekend.
No, I haven't. Let me, you can see the slides have some corrections to be done. So let me do those corrections, then I will share. But the video will be shared today.